right, so let's get started. We have Jessi Cisewski giving a guest lecture today. Jessi is an astrostatistician at Yale. She's worked on a lot of problems in astrostatistics, but in particular she's worked on approximate Bayesian computation and applying ABC to astrostatistics problems.
Great, thanks, James. Yeah, so I'll be think of this as an introduction to ABC or approximate Bayesian computation. I, of course, have various slides, but there aren't tons and tons of slides, so lots of questions are fine. It's better just that we don't move on to the next slide until people are, until you get what's on the current one. I also have some code which, if there's time at the end, I can show how to run some of these algorithms. So our goals today are just approximate Bayesian computation. I was going to add all the different aspects, but we'll just say that's our goal. So at the end of this, the hope is that if you wanted to do ABC, at least on a simpler problem, you would have some sense of how to do that. And my understanding is that last week, Tom Laredo gave an introduction to Bayesian methods. So I'm going to just assume that there's some familiarity, at least, with that framework. And just to make sure the notation is clear, for Bayesian methods, the inferential goal is often to get something called the posterior distribution, which is a distribution on the parameter space conditional on the data that you have. And the posterior distribution is proportional to the likelihood function times a prior distribution. I note that prior distributions allow you to easily incorporate beliefs about the parameters of interest. It's not really easy. It's just if you happen to have a prior, you can see that it just appears there. But actually getting an appropriate prior is a whole question on its own, and we won't get into that. So we'll just assume we have prior distributions. And as I noted, the posterior distribution is a distribution on the parameter space. So once you have a posterior, you can do all sorts of inference. You can get point estimates, you can get interval estimates, and things of that nature. Okay, so we have this form. Now, as we saw with, this doesn't actually appear. Okay. The form of the posterior is the likelihood function times a prior. Now, approximate Bayesian computation is something that can be used in a case where you do not have a good sense of what the likelihood function is. So we're going to call this a likelihood-free approach to approximating the posterior distribution. But as you might imagine, there is a likelihood somewhere. We're just not specifying it. It might be really difficult to write down in a functional form, but that doesn't mean it's not there. And instead of specifying the functional form of a likelihood, you end up simulating the forward process. So you come up with a data generating mechanism so that when you generate a data set from this the simulation model, your output is something that you believe is a good representation of what generated your real observations. Okay, so let me just give some, oops, I just turned this. So let me just specify this and then I'll say a few more words about that. So why would we not know the likelihood? It could be that somehow the physical model is too complex to write down. It might be too complex for various reasons. One reason might be that there's some sort of strong dependency in your data that you can capture by simulation, but is not so easy to write down in some sort of functional, workable form. Maybe you have observational limitations. Some observational limitations you can incorporate into a likelihood, but if you have really complicated observational limitations, that might not be as easy to embed in a likelihood. Okay, so questions about this at all?
What do you mean by forward process?
So the forward process is always going to mean the steps for generating your data. So it might be that there's some complex model that some computational physicist came up with that's a black box to the rest of us. but all you have to do is put in some parameters and then it spits out observations. Or it might be that, that you can simulate a data set really easily from some functional form, but then you put that data through a whole bunch of craziness, like maybe there are truncations, censoring, all sorts of different things that could happen. So it's starting from whatever you could put your parameters into, and then everything that happens until you get what would be comparable to your observations out of it. So this is what I kind of just said. So your assumptions would be drawing from your prior. So the assumptions are assumptions on the values of the unknown parameters that get fed into some forward model. This forward model is everything that's happening, that you think is happening to your data. And then you're going to get out some sort of simulated data set. And then with ABC, you end up having to figure out a way to compare the simulated data with the real data. And if the real data is equal to the simulated data in some sense, which we'll be more specific about shortly, then we say the values that went into the forward model and produced this good data set are good values of the parameter. And we're going to keep those values and say, okay, so this is going to contribute to our particle approximation to the posterior. And then you do it again, and let's say the simulated data does not equal the real data. Then you say that was a bad value of theta, so you throw it out. And you repeat that until you have enough values that were good to approximate the posterior distribution. So if you're familiar with doing Markov chain Monte Carlo, you might have 1,000 particles, 5,000 particles, 10,000 particles, however many you think is appropriate to approximate your posterior distribution. It's that same sort of idea here. That's how many values of theta that you want to produce simulated data that are equal to the real data. Okay, so that's the picture form of it. ABC has been used in astronomy in more than the papers that I have specified here, but these are just some examples that later, if you're interested in it, you can go back and read some of these astronomy papers. Let me just, oh, okay, good. But one in particular that I'm going to highlight is this one, likelihood-free cosmological inference with type 1a supernova, and then ABC for a complete treatment of uncertainty. And so I'm going to pull out a paragraph of that paper just because I like how they describe why ABC could be useful. And so I'm going to read it, but so what they say is, with limited spectroscopic follow-up, we must rely on light curve classification codes and photometric redshift tools to maximize the scientific potential of type 1a supernova cosmology with LSST in near future surveys. And then they say these two crucial steps alone introduce a non-trivial component to our probability model from which we construct a likelihood. Right? So there's some sort of fitting codes that you might be throwing data into, and it might kind of alter or change whatever probability model you would use to otherwise characterize your data. And then they go on and say, additionally, there are significant systematic uncertainties, including errors from calibration, survey design and cadence, host galaxy subtraction and intrinsic dust, population evolution, gravitational lensing, and peculiar velocities. All of these uncertainties contribute to a probability model which simply cannot be accurately described by a multivariate normal. So maybe there is a different type of distribution other than a normal that could capture some aspects of it, but then again, maybe there's not. And so while these things can cause peculiar behaviors in a probability model, if instead you are simulating at first from something that's well understood and then do the same things to that data as are characterized here, then you can use ABC.
So I have a question. In terms of actually coding something in a computer,
Mm-hmm.
When you evaluate a model, you're always generating actual values, like set of y's and a given set of x's, whatever.
Mm-hmm.
So, I mean, functionally, how would the computer even know the difference? Like, why is this a distinct method as opposed to just a very semi-empirical model?
You mean in terms of, I'm not following what you're, so why is this a different method than?
I guess what I'm asking is, algorithmically, it doesn't seem that different from having an analytical model in terms of like how you would proceed with a computer. You're still going to just generate a bunch of predicted values to compare with real data. So
if that's what people are doing in order to do some sort of inference, then they're essentially doing ABC. If you have a generative model or some sort of analytical model and you're generating data, then this is basically what you're doing then. As long as it's not going to be a good approximation to a posterior unless you do some specific things, but that's the essence of what's happening.
But isn't that, like, from a computational point of view, even if you have like a perfect Gaussian, which is characterized by a mean and a sigma, you're going to calculate a bunch of particular values in that Gaussian in order to compute your likelihood.
Okay, so the problem is you don't know where on your parameter space where most of the weight is. So you can try all the. I may not.
Well, so I was thinking about a similar question.
Okay.
That I resolved for myself.
Okay,
I'm not
good.
sure if it's exactly.
Go ahead, try it.
Yeah.
Yeah.
So in some cases, like, I have a bunch of y's as a function of x, and I can generate them from my model, and then I wouldn't need to use ABC. But if my data were like just like a histogram of values, and that's what I was trying to simulate. Like right now, I'm working on a problem where, say, I have a histogram of planet properties. Then even if my model can make planet properties, in this case, there's no dependent variable, so there'd be no real way to compare exactly to there would be no way to write down a likelihood function unless I assume that the distribution had some particular functional form.
So I don't know, yeah, is that
like,
what you were?
Maybe another example, if you had some distribution, some observed distribution of redshifts for your galaxies, then your model made fake galaxies with a distribution, but it's not like you can map each galaxy from your simulation to the observed galaxies. It's just that you want them to have the same redshift distribution. Then, like, you might do a KS test or something to see if they're the same. This would be like a better way to do that.
Yeah. So, yeah, go ahead.
Because you're varying, like, your model has tweakable parameters like dials, and you can vary those dials until you get a match between your model and your data. I think that's what Monte is.
Yeah, so about that, so suppose you have, let's just say, 4 parameters. So you have this 4-dimensional parameter space, and currently you just, let's just say you have uniform priors within whatever that volume is. What you end up doing is trying to find the region in that parameter space that produces data that are close enough in some way to your real observations, but you don't want those values are not going to be. It's not going to be one value for each of those parameters. It's going to be a distribution. And what you're trying to do is when you're trying to quantify the distance between your actual observations and the simulated observations, you want to make sure that comparison is retaining all the information that's needed for inference on those parameters. So it's not the same thing as just generate. So I could just generate from all over my parameter space and get a whole bunch of realizations and compare it to my real data in some way. But that's just some sense of your, it's sort of trying to just figure out what's your uncertainty in the parameters. You're not quantifying the information from your data and using that in order to in order to constrain that parameter space. I don't know, does that, so it's, what ABC is doing, it's connecting what's going on in your parameter space and trying to use the information in your data to kind of go back into the parameter space and say, what are, given your data, the reasonable regions.
Sorry, I don't want to hold up the rest of the class.
but
Is it the case that like your model doesn't make an exact copy of your data that you can compare point per point, and instead it makes something like your data, you want to see if they're similar, like it makes a population of things?
Yeah, so what this should be doing is producing, I'm going to say this and then it's going to have to be modified, but you should be producing exact copies of your data. Like that's what the true posterior should do. It's just, it's not going to be computationally feasible, we'll see. And so, so you can get a sense of the uncertainty in your parameter space. And then I think often what goes on is you pick then the, suppose your data is a function, then you can pick the parameter values that are like closest somehow to the real, well, I guess we usually or often use the chi-squared, and then you can do sort of frequentist methods using that, but you're not ultimately getting your posterior unless you do your distances appropriately. So maybe when I actually talk about the basic algorithm, you'll start to or maybe
maybe it'll become more obvious to me how it's different.
Yeah.
Right now I'm not seeing it.
Okay. Okay, so the basic ABC algorithm is just as I said before. So first you draw from your prior distribution. Then you're going to generate a proposed data set. And that proposed data set is going to be, so I'm just letting F represent the forward process, so the data generating mechanism. And so given whatever was proposed from the prior, you're going to throw that into your simulation model and get out some sort of data set that's comparable to your real observations. And then if the real observations equal the proposed observations, then you're going to accept that value. And you just keep repeating that until you have enough particles to produce a good approximation of the posterior.
So far that is identical to just, even if you had an analytic function, that's exactly what you do to compute a chi-squared or whatever.
Yeah, so you can, one could use a chi-squared distance, but that's not necessarily going to be the best distance to use. It's probably not actually even a good one.
But I think it's different than chi-squared, because in chi-squared, in this fx given data proposed, you would have just x observed would be there, and then you'd be
But I think it's that the chi-squared would be in this step, right? So Sheila's saying, you can produce a simulated data set, and then she's going to say, okay, well, let's compare now some sort of distance between the observed and the simulated data, right? That's what you're describing.
I think the difference is that when we're usually fitting models, when we write down a chi-squared, is the observations minus the model, right?
Yeah.
It's not observations minus a simulation from the model.
Sometimes it is a simulation from a model.
In this case, it is.
No, but what you're describing, I thought, is it a model or is it a simulation from a model?
I'm not sure I understand what the distinction between
Is it for a particular parameter? Is it random? Is the model producing something that could change if I ran it again, even with the same value?
So I guess the most familiar example that I work with is stellar population modeling.
Okay.
Where you have a bunch of input parameters. You could like make a grid of parameter values.
Okay.
And then your forward process generates a bunch of output parameters, which you then compare to the observed parameters.
So with the grid, if you pick one value on the grid and you ran it through whatever that model is, would you get different?
It's not a random number generator.
Oh, okay. So this is random.
Oh, okay.
So this is trying to produce like a random realization.
So f of x given theta prop.
Yeah. So Casey, yeah.
Out the same way twice.
That's right. Yeah.
That's the difference.
Yeah.
Got it.
Yep.
But I mean, also, if you're doing a chi-squared fit, you're implicitly assuming that you have a specific likelihood, which might not be a good case. If you have correlated errors,
Yeah.
then a chi-squared fit just isn't appropriate at all.
Yeah.
So.
Yeah, I mean, in the usual Bayesian calculations, you are doing a comparison of the observed data against all the distributions from the distributions of data from the model given a certain set of parameters, but you're not actually numerically producing all the simulations because that distribution is encapsulated in likelihood function.
Yes.
Right?
Yeah.
So the difference here is that comparison is happening analytically in the Bayes theorem part. Whereas here, because she can't actually evaluate the likelihood function, which compares the observed data against the whole distribution of possible simulated data, which you didn't actually simulate, but it's implicitly there. You need to actually simulate data.
So,
Yep,
so you
that's
can't
right.
compare the data themselves, you have to compare the distribution of the data with the distribution of the simulation output.
Yeah, so that's going to get into one of the major issues with ABC is how do you compare these two things? And so yeah, so I'll get to that soon, but yeah, so that's going to be a question.
So yeah, so then the random number generator in step 2 is the key.
Yeah.
difference, really.
Yep. Okay. Cool. Anything else? Okay. So in the third step, we accept the proposed theta if x observed equals x proposed. Now, even if we have one observation from a Gaussian distribution, it would take us forever to continually generate from a Gaussian and until we get another one that exactly equals it. I mean, it won't take forever because we don't have infinite precision, but you get the point, right? Like so. Even if we only had one observation, trying to wait until we generate another one for a continuous random variable would not be feasible. So instead, what we do is we're going to accept the proposal if the observed data set is close enough to if the proposed data set is close enough to the observed data set. And by close enough, it's going to be quantified by this tolerance parameter epsilon. Okay, so that's part one. So we're giving some kind of we're allowing them to not be exactly equal, basically. But additionally, even if we had we do this, if x is high dimensional, so if we have lots of observations or if our data set is high dimensional, we would have to make epsilon really large in order to make this computationally feasible. So instead of using the raw observations, we often will reduce the dimension by comparing summary statistics instead. So given your data set, maybe you have one-dimensional data and only one parameter, then you might just think of comparing something like the mean. And then you still have your epsilon, your tolerance. Okay, so now this is saying we're going to not compare the full data set, but instead some lower dimensional summaries of our data. And then we're not going to say they have to be exactly equal, but instead they just have to be close enough. Okay, so let's look at some simple examples. We're going to look at examples where we know what the forward model should be, in that we know the likelihood. So in this case, we're going to know what the true posterior is, so we can compare it to our ABC posterior. So in this case, we're going to have n observations coming from a Bernoulli random variable with unknown parameter theta. A Bernoulli random variable is a random variable like a coin flip. It's either going to be 0 or 1, either heads or tails, and it's 1 with probability theta. So if we have n of them, that means we have n outcomes that are either 0 or 1. And the probability, again, of any of them being 1 is theta. So n is a sample size, and this just says theta is a probability that y is 1. If you sum Bernoulli random variables, you get something called a binomial random variable, and we can write out the likelihood in this way. So our forward process is going to be the binomial distribution, and so again we know the likelihood, and so we're going to simulate from the correct thing, but it's only so we can do a good comparison, or so that we can clearly see the difference in the ABC posterior and the true posterior. And so for the distance function, we're going to use the sum of the real observations, y, minus the sum of the simulated observations, x. Okay? And so if the distance is 0, that's saying that the simulated data had the same number of 1s as the real data. In this case, we're going to actually set the tolerance to be 0. And this is okay because in this case we have a discrete random variable, so So it's not unheard of to do this. We're going to put a uniform prior on the parameter theta. So theta is a probability, so it should be between 0 and 1. And then we have a uniform, which is also between 0 and 1.
What is y here?
So y, so that.
The one in the third step distance.
So y, so x, they're each just going to be the sums of the ones and zeros. So it's like the binomial realization. Okay, so this just shows some code, and it's in R, so I'm sorry if you don't know R, but it's just to show you how the algorithm can be implemented rather simply. So up here, I'm just specifying the various quantities. So I'm going to say the sample size is 25. That's the number of observations, so that's the number of ones and zeros. I'm going to say I want 1,000 particles. So it's going to be 1,000 values that I use to approximate the posterior. I'm going to say the true theta is 0.75. So the probability of a 1 is 0.75. I generate the data from a binomial. I'm saying that epsilon is 0. Theta is where I'll store the good values. And then my distance function is just going to be the sum of the y's minus the sums of the x's. And I divide by n, but that's really doesn't matter. Okay, so then this is not the optimal, best, most computationally friendly or efficient way of doing this. But you can imagine that we're going to start at 1, and we're going to do this capital N times. So we're going to do this 1,000 times. And so what we're going to do is propose values from theta that produce data sets that give us this distance. And we're going to keep doing that until we get a distance, d, that's less than or equal to epsilon. So we're going to keep generating our data sets until we produce a theta that gives us a good simulated data set, and then we're going to store it. Okay, so this is the basic ABC algorithm.
Wait, why are we increasing epsilon?
Okay, so I have to, I'm not increasing epsilon. I'm fixing the distance to be greater than epsilon to start this. Okay. Is that what you mean?
Yeah, that's what.
Yeah. So I'm just saying d has to be bigger than epsilon, and then I'm going to keep doing this until it's less than that, until it's less than epsilon. So I could have added 100 or whatever to it. Mm-hmm. So. Okay. So then when I do that, I see that the true posterior is in blue, and we know that because I know the likelihood. And then the ABC posterior is in black. And the true, I say mu and p here. So theta is this red dashed line. Okay, so the key is, and one point in this slide is to say, we're not trying to center anything on the true value. We're trying to get the true posterior. So this does capture the shape of the true posterior. It's a particle approximation, so we get some variability as expected. We only have 1,000 particles that's approximating it, and so it's capturing what we'd want it to be capturing. And then if I increase the sample size from 25 to 100, we see, I don't actually know why I added these plots in, but you see that it's still capturing what it should. This isn't a surprising result or anything, but and then if we increase the sample size from 25 to 100 to 1,000, it's still matching what it should.
Does the number of projections of the thetas increases?
I would expect that, so I didn't check that, but in this case, it probably does. That would make sense, because you can get more variability in your means. So, okay, any questions about this? So here's a Gaussian illustration. So in this case, we're going to have 25 draws So that's independent and identically distributed draws from a normal, where the normal, or Gaussian, has an unknown mean mu and a known variance 1. I'm going to use the sample mean as the summary statistic. So that's adding up all the values and dividing by, in this case, 25. And so then I'm going to just do the absolute value of the difference between the proposed and the observed sample means. And I'm going to show you what happens when the tolerance is 0.5 versus 0.1. And I just use a Gaussian prior. Okay, so in this case, again, in blue, we have a true posterior. The true value for mu is in red. And then this is the ABC posterior when we have a tolerance of 0.5. So we see it's rather deflated because the tolerance is so high that it's just kind of washing out. It's accepting more data sets than it should in order to match the true posterior. But when we decrease the tolerance to 0.1, we see that it matches much better. Yeah?
So in the case, when the tolerance is higher, is it always the case that the I guess, bad approximate posterior would at least be centered at the same place as the true posterior, but maybe just be wider, or could it just be like really far off as well?
Yeah, so where the ABC posterior is centered depends a lot on what you're using for your summary statistic. And if you use a bad summary statistic, it can be really far off. Does it generally, so if the summary statistic is the same, could it ever be centered somewhere else? So I suppose in some, you could come up with some example where that happens maybe. It's not obvious what would.
I was just thinking, because you won't, for a real case, you wouldn't know if the true posterior and the ABC posterior are close. But you wouldn't be able to say, like, well, physically, if my uncertainty on this parameter is within this range, then I might be okay with that, even if it's approximate.
Yeah.
Learn something about the physical value.
Yeah. So that's an interesting point. Yeah, it would seem that that could be a reasonable thing to consider. Just what range of uncertainty do you care about?
Yeah. It was obviously wider, but maybe you don't care for a specific problem.
Yeah.
But I think the choice of this summary statistic being the mean enforces that. But suppose you had chosen this sample standard deviation as your summary statistic, then it's not so clear that it would.
Oh yeah, no, that's what I said. So that's I said so where it's centered depends on the summary statistic. So even if I use the median will be shifted unless the sample mean and the sample median are really close. Yeah.
Is there a way to select summary statistics so that you can enforce that they would be centered at the same?
So what's tricky is in practice, you know, I guess the idea is that you know so little about your model that you have to simulate from it. So there are ways of trying to check, to try to throw it off. Like you could try different summary statistics and see if it's shifting around. But selecting good summary statistics is actually rather difficult. But so, yep.
If you took your summary statistic to be like a distance between those two distributions based on maybe a coarse histogram, would that help you converge faster?
So the distance between
your data and your target.
Yeah. Okay. So the a summary statistic where instead you look at like the distribution of your data, like so you can do distributional comparisons, like looking at the empirical CDF and comparing that somehow, or looking at a density and comparing that somehow. So that, to me, that's a good way of comparing it because it's somehow using the distribution of the observations rather than some fixed summary statistic.
So it'd be closer to like what they would call a sufficient statistic.
Yeah. So actually, is that? That'll come up. So, in a perfect world, we would know the likelihood, and therefore we could figure out sufficient statistics. But we wouldn't need to because we have a likelihood, and then we could just do MCMC. So, because in this with ABC, you don't have a likelihood, and actually in general, the best sufficient statistic one could come up with, given a data set, would just be the order statistics, which is high dimensional. And so in this case, the reason this works nicely is because the sample mean is a sufficient statistic for the Gaussian distribution, and then for the binomial, what I was using for the summary statistic, also basically the mean, is also a sufficient statistic. But when you get to the real applications, you don't have sufficient statistics. If you did, you would use those. But again, if you did, then you'd have a likelihood, and then you wouldn't do this. Yeah, so it's, but yeah, so like what you just said, the distribution though it has that information like what the order statistics would have. So,
I mean, you could make a sufficient statistic if you did a CDF, some kind of a CDF, and you sorted all the data and you made a CDF,
yeah.
and you binned it such that the binning is fine enough so that there would only be one jump at each,
yeah.
a maximum of one jump.
Yep.
Then that would be a sufficient statistic, but that would be high dimensional too.
Yeah, but instead you could try to compare functions. Like I would actually smooth over that instead, and then compare the functions. Yeah, so that, and I'll be using something like that later in this.
There's
Yeah.
also some not necessarily smoothing ideas, but like distance metrics between functions, between empirical CDFs. They use a lot of non-parametric things like Kolmogorov, Smirnov.
Yeah, it turns out with the KS distance, so this is just what I found for simple examples. It bottoms out before it converges, and it's somehow really hard to shrink it further. So, but if you smooth over the empirical CDF, but still do like a KS distance, it actually does well for some reason. But yeah, there are all sorts of functional comparisons.
I mean, just the maximum distance between the smooth distribution.
Yeah. So in other work, I've used that. Yeah. So you can do a Hellinger distance. Which would be between KDEs, some sort of estimate of the density. You can, like you were talking the other day about a KL distance. So yeah, there are lots of different things one could try. So okay, cool. Oops. Okay, so now I want to get into some intuition about what's going on with ABC and why we even do what we do here. And so this example comes from Chad Schaefer, who's a statistician at Carnegie Mellon, and so these are the steps we've seen before. If one wants to generate a draw from a posterior, you draw from the prior. You draw this if you had it from the density or the likelihood, and then accept the proposed theta if the proposed data equals the observed. And so why do we do that? Well, so let's let this theta ACC be the accepted theta, and theta prop just be the proposed. So for any value theta, the probability that the accepted value, that it equals the accepted value, is just saying it's what has to happen for this is to say that the proposed theta equals that value, given that you got a data set that equaled the observed data. And if we just deal with use some properties of conditional probabilities, this turns into this. And this is saying the same thing as our density or likelihood here, which just gives us the posterior. Okay, so if theta is discrete, we can go through this and see that accepting a theta based on what's going on here gives us what the posterior would be. Okay, so again, this step from here to here is just using some properties of conditional probabilities. Okay, so then we can also consider the same idea if we have a continuous theta. So we can't say it exactly equals something because that probability is 0. But we can say the probability that our accepted theta are in some set t. Well, it's accepted if it was proposed and it produced a data set that equals the observed. And then we can go through the same exercise as with the discrete case and see that, that this probability is the same based on the steps outlined here as integrating across the set T, integrating the posterior distribution. Okay, so now just from here to here, I got rid of the normalizing constant and just called it K. And the reason to do this is just to see that that this thing. So I'm going to change something in a second, but we're going to be focusing on what's happening here to here. So in this case, we are accepting if the proposed data equals the observed data. But now what if we're a bit more ambiguous about what's going on? And we just say we've accepted that proposed value, right? So various things could happen for accepting. We could have produced data, simulated data that were close enough to the observed data. And then this thing here is going to equal this only if somehow, let's see if this, only if this probability, the probability of accepting the proposed theta is proportional to what would otherwise be the likelihood function. So if the acceptance probability is proportional to the likelihood function, we're going to get something that, that matches the true posterior. I'm going to show some figures of this too. So what's the point here? What I just said, if theta accept is a draw from the posterior, if this thing is proportional to the likelihood. Okay, so it gives us a sense of how good or poor our approximation to the posterior is. And the ideal setting would just be, okay, well, if we could accept this, if they were exactly equal, then we'd be fine. It's just that would not be computationally feasible. And so we've already discussed this, but the alternative is instead to say, let's just get data that are close enough. And so we end up with this tolerance epsilon. And then if epsilon, assuming the summary statistics that we are going to be using are good in some sense, then if epsilon decreases to 0, then this probability will converge to something that's proportional to the likelihood. And then that's great, yeah.
I have a question.
Yep, sure.
This will come up later, but what if you do have uncertainties on the observed x's? Would you want to put that into your epsilon somehow?
Yeah, so if you have uncertainties, you can, so I was going to say you can build that into your forward model, right? So,
yeah.
but
You can also put in the distance metric, couldn't you?
yeah, so that's why I just paused, because I was like, so you would build in the uncertainty into your forward model anyway, yeah, but then somehow you'd want to capture that in your distance, because you don't want to then, in order to somehow appropriately compare the simulated and real data, yeah, you'd have that sort of kind of cushion somehow. It would require some thought, though. It's not straightforward necessarily how to do that, especially once you get summaries of the data and you're no longer looking at the individual values. But if you're comparing the distributions, you might be able to get kind of a band around it. So yeah.
You'd have to do some kind of relaxing the distance metric a little bit to accommodate the uncertainty.
Yeah, so that seems like what one would have to do indeed. Like, so I can imagine if we were trying to reproduce the exact data, you would look at each observation and then somehow try to do some comparison, observation to observation, by incorporating that uncertainty. But you're not going to be doing that, and instead you're going to be comparing some sort of summary. So now what I'm picturing is like your empirical CDF, but having some kind of like band around it. But then also with your simulated data, you'd want to have that sort of band, and then somehow you want to compare kind of thick functions somehow. So, okay, so let's look at a little toy example. In this example, we're going to go back to a Gaussian or a normal distribution, and have it come from a Gaussian with a mean of theta and a variance of 1. And we're just going to have one single observation in this case, so we can kind of see what's happening. So if the true theta is 0 and x observed is 1, then so what I just said, forget that. If we draw or propose a theta that's 0, then we're gonna, and we are using the Gaussian distribution, assuming that we know the forward model in this case, then what's gonna happen is, so drawing a theta and using that theta in our forward model, so we're using that as a center of the forward, of the Gaussian distribution. And since the observation that we have is equal to 1, and if we use an epsilon of 0.1, that means that the probability that we would accept a proposal with this theta and this epsilon and this observation is the area under the density between these two vertical lines. Okay, so given all of this, the probability that we would accept the theta here is going to be whatever that value is. If we propose a theta that's 1 and our observation is still 1, then that probability is going to be the area under the density between these two vertical lines. Okay, so this is just trying to explain what we mean by the probability of accepting a value.
What's phi again? Sorry, phi and
so this is going to be 1 if the distance between these two is less than epsilon, and it's going to be 0 if they're further away than epsilon. Yeah, sorry, I didn't actually say much about it, but it's just this function. It's like it's an indicator. Okay, so if we did this sort of exercise for all the different possible thetas, we can compare the likelihood function, which is in blue, with the acceptance probability, which is this red dash line. Okay, so when epsilon is 0.1 here, we see that the likelihood and the acceptance probability match really well.
You don't really need them to match, right? You just need them to be proportional.
And actually, that is what. So they are just proportional. I had to reweight them so that the area under each of them was 1. But now, what if we make epsilon a bit bigger? So if we make epsilon 0.4, then we can go through the same exercise and say, okay, what if we drew a theta that was 1 and our observation is 1? So now the probability of accepting a proposed data set with this theta is larger because epsilon is larger. There's more area under the curve. It's more probable that we're going to get a good data set. And same thing here, right? So we can get the probability of a data set being proposed that's when theta is 1. And so now, though, we can see that the acceptance probability, if we do that same sort of thing, is not matching the likelihood as well, right? There's a difference between the acceptance probability and the likelihood. Okay, and if epsilon is 1, it gets even worse. So this epsilon is important, and you want it to be small, is the message. Questions about this illustration? So the point here was just to say that if the probability of accepting a theta is proportional to the likelihood, you're going to get something that's a good approximation to your true posterior distribution. Okay, so getting into the summaries, a statistic is sufficient if this holds. So if you have a density and you condition on that statistic, if that equals a density without the independent of the parameter, then it's called a sufficient statistic. So and if that holds, we see that our density with the full data set is going to be proportional to the density with the sufficient statistic. And this is great, except for ABC, you're not going to have sufficient statistics. But it's just to illustrate that in statistics, sufficiency has a very precise meaning, and so it's just to be aware of that, I guess.
I think sufficient means that the likelihood only depends on the data through the sufficient statistics.
That's right, yeah.
So then the first, on the right-hand side of the first equation should be, is proportional to some function of s of x given theta, right?
No, I think this should be, so this is fine. You can, so it's just saying if you take the density and you also condition on the sufficient statistic, like if you think of a Gaussian distribution and condition on x bar, then you can see that that you're going to get something a distribution that's independent of the mean, for example.
Here, x is not observer value. It's just a dummy variable showing that it's a curve.
Okay, so
You're just warning us not to use it in the English language sense of sufficient.
that's right, yeah. So if you do ABC and you say, oh, I have this sufficient statistic, you probably don't. And if you're doing ABC, and so just say you have a good summary statistic that you think is informative. Do I have?
I don't know if this is another jargon term, but would it be back in the realm of English to call it quasi-sufficient?
If you have a measure for what you mean by that.
Well, I mean, just that it's going to give you something proportional to the likelihood.
And the problem is you don't know the likelihood, so you don't know it in practice, right? So I would just, so in the ABC literature, you would just call it a summary statistic, and you hope that they're good, is basically what happens. So in a nutshell, ABC, the basic idea behind ABC is that you're using a representative enough summary statistic. Uh-oh.
Representative enough, then, is what's replacing.
Yeah. Oh. Yeah. Coupled with a small enough tolerance should produce a good enough approximation to the posterior. So I like this because, I mean, like, ABC can be very useful, but, like, there are also a lot of issues with it, right? So if you don't have good summary statistics, you can get things that are completely off what the true posterior is, and you just won't know. And so, so there are ways of kind of building confidence in the summary statistics you're choosing by using simpler models and finding summary statistics that give you ABC posteriors that match the true posterior in those simpler models. But then you still have to make that step to the complicated model and say, oh, I hope these still work. So that's, just consider that more of a caution. So first, any questions about what's been discussed so far?
Do people use, like, I don't know, cross-validation or something like that to figure out this tolerance epsilon?
So we'll get into the tolerance. Yeah. I don't know that one would use cross-validation, but you do want it to be small, and how to decide if it's small enough is a question that there are some solutions to. Okay, so how to pick the tolerance. And so this is going to get into, I'll just say, generally sequential ABC. And the idea with a sequential version of ABC, and one in particular, which is this Beaumont et al. 2009 paper, where they use a population Monte Carlo version. And so the idea with this is that you want your tolerance to be small, but if you just start off with a really small tolerance, then it's going to take forever to get good values from your prior. And so what you can do instead is start your ABC algorithm with a tolerance that's not super small, and you run it, and then you get your ABC approximation to the posterior. You get your particle approximation, and you say, okay, I want to do this again with a smaller epsilon, but I want to somehow use the information in that first step. So you, in the second step, instead of drawing from the prior, you draw from the previous step's particle system. Okay, so so you would just, maybe you have 1,000 particles, you can draw among those 1,000 particles, and then you can do something else to it, which I'll explain in a second. But then you get your ABC approximation in the second step. Now the problem is, if you don't adjust for the fact that you're not sampling from your prior, you're not going to be targeting the correct posterior. So in order to target the correct posterior, you're going to want to use something like importance weights. And what importance weights do is it weights your particles so that it shifts it and still targets the correct posterior. So I'm going to say a bit more about importance sampling, but the message is just that you can't just sample from the previous time steps particle system, but you have to make some sort of adjustment so you're targeting the true posterior, which requires that you are sampling from the prior. Okay, so we'll get into that, but then ultimately what you end up with are your particles, so the actual values of your parameters, and then weights attached to that. Okay, so I'm going to just say a little bit about importance sampling, but first just some reminders about Monte Carlo integration, or Monte Carlo sampling, we'll say, and what happens with importance sampling that makes it different. So in general, with Monte Carlo methods, you're simulating from some distribution of interest, and you might put those values into some other function, but ultimately you rely on the law of large numbers in order to estimate whatever quantity is of interest. So this just gives some details here. So it's a form of stochastic integration, and you can approximate expectations by just generating values and then doing something to it in order to get the estimate of interest. So for example, how do I define W here? Oh, okay, those are the weights. Let me go to the next slide, so it's going to be a better example. So let's suppose that we want to estimate a probability, and we want to estimate the probability where the random variable is coming from a standard normal, so a normal centered at 0 with standard deviation 1. So we want to estimate the probability that y is less than or equal to little y, which we can also write as an expectation of an indicator function. Okay, so this expectation is what we want to approximate or estimate, and so just in general, we can see that, or we know that the CDF of this random variable y less than or equal to y is the integral from, since it's a Gaussian, negative infinity to this cutoff y, integrating the Gaussian density. And so we can also instead write this as negative infinity to infinity and then incorporate an indicator function so that it's going to be 1 if the values are less than this cutoff y and 0 otherwise. And so in order to use Monte Carlo sampling, we can draw some large number of y's from a normal distribution, because we know how to sample from a standard normal. So we can do that. And then we put those values into our function h here, which is an indicator. And so what we do then for our estimate of this integral is just count the number of draws that are less than our value x, which, shoot, this should be y, so less than our y. Right, so we've all, I'm sure, done this before, probably many times, and maybe without even thinking that this is what we were doing, but this gives us an estimate of that expectation. With importance sampling, so this works nicely if we can sample from the distribution that we're targeting or is of interest. But that's not always the case. We can't always sample from what we want to be sampling from. So what do we do if the target is either not available or for whatever reason you don't want to use it? the idea of importance sampling is, rather than drawing from our target distribution, we draw from some proposal distribution. And so let's suppose this function here in blue is our target. This is what we want to produce a sample from. But for whatever reason, we can't. It's a standard normal, so we really could, but we're just pretending here. So we can't sample from that. But we do know how to sample from this pink distribution. And so what we can do for importance sampling is sample from our proposal, which is easy to sample from. But then we have to re-weight those draws, so we're still targeting the desired distribution. Okay, so rather than sampling from this blue one, which we want, we sample from the pink one, but then we somehow have to re-weight it so that we're getting the right blue distribution. So how do we do that? Well, oh yeah.
The pink distribution, is there a rule about it? Like, does it have, like, what if you used a uniform distribution? Would this algorithm you're about to describe, would that still work?
So it works. The problem with a uniform, so a uniform's fine if you have a finite range. But if you're going from negative infinity to infinity, if you use the uniform, you're just going to be cutting off the tails, which, like, maybe it doesn't make that much of a difference, but the usual the usual criteria for the proposal is that it should cover the same domain as the target, and then in order to reduce the variability of your estimate, you want it to have the same shape. That doesn't have to be the case, but you just get better estimates if it follows the same shape as the true one.
But in this case, we don't even know anything about the target, so.
You have to know the functional form of it.
I thought that we are working in a regime where we don't know the likelihood function at all.
So this isn't for the likelihood. Our target's going to be the prior distribution, and the proposal is going to be the previous time steps particle system with some adjustments. So in that case, we could sample from the prior, but we're going to choose not to.
I see.
Yeah. So that's what, so often people use importance sampling when they can't sample from the target. Like sometimes it's a really complicated distribution, but you can also do it for other reasons, which is the case for the ABC, sequential ABC. Okay, so then what happens? Well, we still want to approximate this integral where we have some function of our random variable y times the density. But we're saying we can't actually sample from the actual distribution f. And so instead, we're going to sample from G. But since we're sampling from G, we want to make sure that what we want is equal to, so we want to make sure that by sampling from G, it's not affecting our estimate for this particular integral. And so what we see is that since we're actually instead sampling from G, what happens is we end up with this quantity f of y over g of y, and this thing here is going to be our importance weight. Unnormalized, you still have to normalize them. But if we include this thing, then we're going to still be targeting this correct distribution. So this is the kind of mathematical form, but how we actually then would estimate the integral is, so it's still appearing here. So now for our Monte Carlo estimate, we don't just have our h of y's. So previously we had our h of y's, but now we have our h of y times this importance weight, f of y over g of y. And so our particles have to be accompanied by these weights, so that if we want to target our actual integral of interest, I, or expectation of interest, I, we have to look at a weighted sum of what's going on. Does that make sense? So what I was just saying this before, but for us with ABC, the target is the prior. We want to be sampling from the prior, but the prior makes it so that the ABC algorithm is slow. And so instead, we're gonna actually sample from a better estimate, and then include these importance weights along with it so that we're still targeting the true posterior.
So how do we?
Not a better. Is it better estimate? It's not better.
Faster.
Faster.
Okay.
Yeah, faster. Thanks.
Where's the information from the true posterior entering into this?
So what we end up with, so the y's are like our particles. The y's are like our thetas that we're drawing. And so, so if we wanted, for example, estimate the mean of the posterior, we would have our thetas times the importance weights. So the posterior itself is the ABC posterior is a particle approximation, and instead of each particle having weight 1 over the particle sample size, it now has weight prior density at y over what we actually sampled from, which is the previous time steps particle system.
So I understand that our proposal distribution, for various reasons, we might want to use something that's different from the prior distribution.
Mm-hmm.
Is maybe you'll get to this only. Is there some distribution that's really good to use in ABC?
Yeah. Okay.
Like,
So
is that
yeah.
where this will come in?
Yeah. So So what I'll show the algorithm in a second, but yeah, it's not going to just be a straight sampling from a weighted, basically like a multinomial distribution, which just is a value with a weight. But we're going to select a value according to the weights, and then take that value and do something to it, which I'll say in a second.
Okay.
So what it comes down to is how do we build a good proposal distribution from the previous time steps particles, and their weights.
Faster is it doing this?
It's so I don't have an exact value. It's just so if you try. So I've done some simple comparisons where let's suppose you just want to do this for a simple Gaussian case, and if you set the epsilon to be something really small, and just run the basic ABC algorithm, you can time that, and then do the same thing sequentially. And doing it sequentially, I'll just say, is much faster. But it's not going to be always faster. So it's a hard thing to actually quantify, but it tends to improve the computational speed. So, yeah, I've not seen.
Agree.
What's that?
And they always agree.
Well, all else equal, unless something's set up improperly with this proposal, they should agree. Yeah. Okay, so this is going to give one illustration of importance sampling. So if we want to estimate the probability that y is less than 0.3, where y is this function that's kind of the dotted/dashed magenta curve. So that's what we want to be sampling from. And we want the probability that this thing is less than 0.3. And we can try out two possible proposal distributions. Uniform 0, 1. So just as a side note, the function outside 0 and 1 is also 0. So this is just to show what can happen if your proposal distribution is much, if it's not perfectly, well, it doesn't have to be perfectly aligned, but if it's pretty different from what your target is, right? So we have a uniform between 0 and 1 that actually seems to cover the region pretty tightly, which it does. That's intentional. And then this blue one, which is uniform from 0 to 4. And so this is just this is less related to ABC and more just to explain something about importance sampling, because importance sampling on its own can be something that's really useful. So if we take 1,000 samples of size 100, so I'm repeatedly getting estimates of that probability for each of the possible proposals. And so if we do that and then look at the distribution of those values, we see that the uniform 0, 1, so they both are more or less centered on the true probability, which is this dashed magenta line. but that the uniform 0 to 4 has much more variability in the estimate than the uniform. So I guess the point there is just if you're doing importance sampling just for its own right, that it's good to have proposals that match pretty closely to your target. And so this shows the expected values, and then the variance is roughly 1/6 of the variance of the better proposal. Okay, there are extensions to just importance sampling. There's sequential importance sampling, and then there's sequential Monte Carlo or particle filtering methods. And so those are just, so suppose you're in a situation where you're sampling from a complicated posterior or a posterior that's changing with time. If your posterior is changing with time, doing MCMC means you have to restart every time, at every time step you have to get a new MCMC posterior. But sequential Monte Carlo allows you to update the posterior in time, so you don't have to recompute the whole mess. So these are other techniques. And then of course approximate Bayesian computation, which we're talking about.
When you say changes with time, could you use time more generally to be like, if you condition on one parameter value, you get a posterior, and then you change that parameter slightly, and then you want a slightly shifted posterior? Or is that
so you're saying the parameter itself is changing with time? Which
I guess I'm asking how in practice when people are using that, is what you're referring to as time usually actually time?
Oh, okay.
Could it be something more?
Oh yeah, it could be. So yeah. So actually, so in my dissertation, rather than time, I just was because of the nature of the distribution we wanted to be sampling from, I had to add in the observations one at a time. So I used those techniques so I didn't have to recompute everything each time, but instead could do it sequentially. So I was just adding, I had a fixed data set and I just added them in one at a time because it was doing something complicated. But yeah, so it could just be something that's changing for whatever reason. I feel like one example that I remember people talking about was with a jet flying, and it'd be sensing something that needed to be computed really quickly. I don't know more than that, but they needed to make some sort of inference fast, and so something was changing with time. Maybe it was air quality. I don't even know, atmosphere stuff. But they needed it to be done quickly. So there were time examples, but it could be something else.
Well, for example, if your data set is too big to hold in memory, you might want to
Yeah.
add in data and then update your posterior.
Yep, exactly. That's a good idea. Yep.
So suppose I have a dumb prior, like I won't even, so I'm just using a flat prior or something like that.
Okay.
What intuition helps me to choose the G? I mean, how do I figure out what G to choose?
Yeah. Okay, so that's going to be in 1 second. So so message importance sampling can be used for ABC to improve computational efficiency. I can't say explicitly what that improvement is, except I will always use it because if I get down to the epsilon I want, just using the basic ABC, it seems to run forever and never converge it. Like just in some simpler examples. So, but this sequential version makes it really does improve things. I'm sure there could be some examples where you don't want to do this, but it tends to be a nice version of ABC. Okay, so what does this ABC PMC or population Monte Carlo algorithm look like? Well, let's step through this. It looks like a mess, but it's. So what happens in this first iteration, the first time step, you just do the basic ABC algorithm that we already talked about, right? You draw from your prior, you accept the values if it produces data sets that are close enough to your real observations. But then at the end, you're going to say, okay, so now I have this particle approximation, and they each have the same weight because we were sampling from the prior, which is what we should be sampling from. But then the problems come in, solvable problems come in when now you have to start doing this sequential version. So I'm going to skip this set for a second, but if we now go to time step 2, and so for time step 2, rather than drawing from the prior, we're going to do this blue line here. And this blue line is saying, I'm going to draw a value from the first time step's particles uniformly because they all have the same weight. So if they have different weights, it would just be according to whatever the previous time step's weights are. And so you draw one of those values. So let's just, in the one parameter setting, we would just have one number now. But if all we did was draw from the previous time step's particles, we're going to end up with a really poor approximation to the posterior because we're going to get a lot of values at the exact same spot. And so in order to make that not happen, we're going to take that value that we drew from the previous time step and we're going to move it according to some kernel. If your parameter is continuous and it doesn't have any sort of restricted domain, one really nice, easy to implement option is just to say, okay, that's just going to be the center of a Gaussian distribution. And I'm going to take that and then move that particle one step according to whatever Gaussian this is specifying, which I'll say in a second. So rather than just that value, it's going to be that value either to the right or to the left. And then that becomes my proposal. And so I'm going to draw my proposed data set from the forward model according to that moved particle. And then you calculate the summary statistics, you compare the distances, etc. And let's suppose that we actually accepted that value. Well, then we need to figure out how to write down the weights, the importance weights. And so what the weight is going to be for observation I is it's going to be the prior at the value that was accepted. But then what we're actually sampling from, our proposal, is this weighted, these weights, according to the previous time steps particle system, it's weighted, and then we also have this kernel, this moving step. So we have a sum of weighted kernels. Okay, so our target is this thing on top. What we actually sample from is this thing in the bottom. And so what we have to consider then is that we could have drawn any of the capital N possible particles according to these weights. And each one of those is, because of this proposal, is going to be a Gaussian density that has a mean, whatever the particle value is that's connected to this weight. And then this is what the value that we kept. This was the particle value for the new time step. And so this is centering and scaling the value, and then this is a Gaussian density, this phi here. So it's a weighted sum of these Gaussian densities. And so if I was not using a Gaussian step here, I would have to adjust what this kernel is, and this kernel would just have to match whatever I'm doing to the particles. Okay, so the importance weight, again, is the target, which is the prior, divided by the proposal, which is this weighted sum of kernels.
So you have to be able to evaluate the prior.
You have to be able, yeah, because you also have to sample from in that first time step. Yeah.
Well, I mean, you can imagine the same situation where, just a tangent, but if you have a likelihood that you cannot evaluate, but you can sample from, you could have a prior which you can sample from but not evaluate.
Yeah, if your prior cannot be sampled from, I think you have bigger problems. So, yeah, I mean, like, so what would a prior be that you can't sample from? Well, I guess some people might use someone else's posterior, and then the question is, how do you sample from that posterior? And you could do like acceptance sampling, and you could do some bizarre things, but yeah, you might have to do some sort of like kernel density estimate of whatever that particle approximation is, and then have this just be the predicted value based on that. So
you also have to use proper prior.
Yeah. So as yeah. So it should be a proper prior. Yeah. So definitely other things can come up, but okay. So then you after the second time step, now you have these weights, and so when you get to the third time step, these weights are going to just be whatever the previous time step's importance weights were. You do have to normalize them though. And then in this Beaumont et al. Paper, they suggest that the variance of this normal, so the size of the step you take, can be a good option for that variance is to use 2 times the weighted variance of that previous time steps particle system. And there are various reasons that they suggest this, but you just calculate a weighted variance and then multiply it times 2, and then you can use that for the step. You could use something different, but that's optimal in some sense. And then with each of the sequential steps, you're gonna be shrinking your epsilon as well. So you might start with a larger epsilon and then decrease it by some, maybe you have a fixed stream of epsilons, or maybe you adjust it adaptively, or do something of that nature to shrink it.
So in the first 2 steps, so in the first step you have some large number of samples from the prior, and then you use your basic algorithm to choose the ones that kind of give good enough matches. But then all the other steps, the number of the particles that survive that are always conserved after.
So you're still doing that same thing. So you're drawing from that, but then taking a step, and you have to produce a data set that gives you a summary statistic that still is within epsilon.
Right. So n is preserved after step 2, because you're always picking the particle, and you're proposing new steps until you get a match.
Yes, yeah, exactly. Yeah, so you have the same capital N because you keep doing this until you get a good one. Yep,
okay.
absolutely.
So you're never like throwing out a particle after step 2.
So you throw out the particles that. So.
Oh, I mean. Well, so what I'm saying is n is constant.
N is constant throughout. Yeah.
After the initialization.
Yeah. Yeah.
It is fixed.
For, yeah, capital N is fixed, and.
Well, I mean, n is the number that survived the first sampling, the basic sampling.
Yeah, and so there's been some discussion too about if it makes sense to increase the n as you proceed. So there are different ways of doing it, but how I have it set, this big N is just fixed, and it's something you decided in advance. Yeah. Yeah.
So now I can sort of see part of the answer to my question, which is how the posterior gets into this, how you sort of get closer to targeting the posterior, and that's because you're accepting, you're doing this only from the samples that you've accepted, and now you're perturbing, instead of drawing from those samples, you're perturbing the samples a bit with this kernel.
Yep.
But so I sort of see that that's helping you to target the posterior, but where does this weight formula come from? Is that?
Yeah, so this is the importance weight. So because we're not so in this step here, we're no longer drawing from the prior, which is what we should be drawing from. And so we should be drawing from this. We actually draw from this. So this is the importance weight that we saw when we were discussing importance sampling. And so this is what's going to re-weight it. So we're still targeting the true posterior. So an interesting exercise is, so I showed some examples of importance sampling functions, but you can try something like, suppose you want to draw from a normal, but instead you draw from a t distribution or something, and compare the samples when you weight it versus when you, according to the importance weights, versus when you don't weight it. And so when you don't weight it, your distribution, your particles are just coming from that t distribution. So it's not going to be estimating the Gaussian. But if you look at a weighted approximation, it should be targeting then your Gaussian. So. And so if we look at the Gaussian illustration from before, this is just showing the sequential version. So the first ABC posterior is this broader one. And in that case, the tolerance was 1. And then as I shrink the tolerance, the ABC posterior starts converging to the true one. The true one is this dotted blue, and the ABC posterior is the sort of lime green. And so you see that it's converging with the time steps to the truth.
What's your algorithm for adjusting the tolerance?
Okay, so so there are several ways for adjusting the tolerance. My recommendation for the first step is, so suppose you want 1,000 particles. I would instead generate 5,000 or 10,000 or 20,000 and keep the 1,000 that produce data sets that have distances that are the 1,000 smallest distances. So that allows you to adaptively select this, because sometimes with different summary statistics and distance functions, which is something that you end up playing with a lot, you don't always know what a good first tolerance is. So if you do that, you can adaptively set the first one. And then to set the second one, there are various ideas. One is to just have it, sometimes people will just have a fixed sequence. Say the first one's 1, the next one's 0.9, the next one's 0.8, the next one's, so you could do something like that, but that's not really adapting to what the nature of the algorithm. Another option is for the second one, so in the previous time step, you have the, let's say, 1,000 distances that resulted in particles that were accepted. And you could take like the 75th percentile of those distances. So you shrink it according to like the 75th percentile, 50th percentile, or something like that sequentially.
And you just keep doing that.
And you can keep doing that. With a PhD student at Yale, we just submitted a paper for a different way of adjusting it. And I can explain that offline if you want to hear more. So there are different ways of shrinking it.
So after you finish this, do you need the importance weights anymore, or can you just treat the samples as if it was like from an MCMC and plot them up?
Yeah, so you need the weights. But the thing about it is the weights should be pretty uniform, but they're still important. So the weights will be generally be close to 1/n, but not exactly. So you should still use those.
Okay. So these things that you've
these are all weighted according to the particle weights. So they're weighted kernel density estimates.
Yep.
Okay, so now I was going to get into a ASTRO example, and this is it's going to be a simplified example, but just to see how one can do this in practice. So this is for the stellar initial mass function, and so the stellar initial mass function. There are many astronomers here. I'm sure you all know what this is, but it's the distribution of star masses that form within a given volume of space. So when a star cluster is forming, at some point we would have the stars form. It's a dynamic process. Like the stars will continue to form for a while, but let's just suppose that there's a stopping point, and we care about the distribution of the masses of the stars at that point. That's the stellar initial mass function. And I'm going to give my statistician version of what's happening. And the astronomers can just ignore this because I'm sure there are lots of things wrong. But if we have our molecular cloud, at some point, something happens where it's going to fragment. And from that fragmentation, stars start to form, maybe protostars, and then eventually stars themselves form. And let's just say the excess gas is either sitting there or blows away. But this whole process is quite turbulent and messy. And I know that there are at least two theories on what's going on and how stars build mass. But from my statistician version, the thing that is interesting to me is that you have this fixed amount, we'll say, of gas that's in the molecular cloud. And in this whole process, like something's going on where there seems to be some sort of interaction between, whether it's between the protostars or between the stars, where it maybe not be explicitly a competition for material, but the neighboring stars could be affecting the available gas for stars nearby. And so one of the reasons ABC was appealing is because generally for the stellar initial mass function, the masses of stars are considered independent draws or are independent from each other. And what we were curious about is if we can somehow capture some sort of spatial dependency and try to build a forward model that describes some aspect of the physical process that's kind of defining the masses of a cluster. So that being said, I'm not going to actually explain that side of things. I'm just going to use what's traditionally done, but there's at least some appeal for trying to use ABC for this setting. And so what we're going to focus on is there's a broken power law way of modeling the stellar initial mass function. And one version of it has a different power law in three different stellar mass ranges. So we have a substellar region, and then kind of low stellar masses, and then higher stellar masses. For the statisticians, the M sun is just one solar mass, which is just the mass of our sun. And so what we're actually going to focus on is just one range of the stellar initial mass function. So we're not even going to consider the broken power law. We're just going to look at the high mass end of the stellar initial mass function. Okay, so this is one example of a distribution of masses. This is from, I believe this was from the Orion Nebula cluster. And I didn't do anything other than bin the masses, even though I always say don't bin your data, but there it is. So what I'm going to do is build a likelihood function trying to incorporate some of the things that affect our data set. And so all this stuff I can actually put into a likelihood, and therefore I can get my a true posterior distribution. And so I'm doing this so that I can determine summary statistics that are seem to be capturing the information that's in the data needed to infer the parameter. So in this case, we only have one unknown parameter, and it's alpha. We have a power law distribution. So our likelihood, just given that, would look like this. Okay, so n total are the total number of stars in the cluster. But then there are all these different observational limitations. One that affects the stellar initial mass function is aging. And so more massive stars die faster. And so if the data that we have is from an older cluster, we're going to be missing some portion of that upper tail. And so we want to account for the fact that we're not observing the full initial distribution of masses, but some truncated version of it. And so just as an example, if our cluster is 30 million years old, the cutoff for the masses of the stars that we would see would be around 10 solar masses. This is just based on an approximation, and so if that's the case, we can build that into the likelihood by including this term here. And then there are also observational limitations. So we're not necessarily going to be able to observe every star that's even still present in the cluster. It could be that one star is next to a brighter star, and so maybe it just looks like a more massive star, or maybe it's being blocked, or maybe there's dust in the way, or maybe they're just not bright enough for us to be able to detect. And so we want to add in a completeness function, which is just going to define the probability that we would observe stars of a particular mass. You might also imagine that there is some sort of spatial dependency here. So you could imagine a spatial completeness function. But in this case, it's just going to depend on the mass of the star. And we're going to say that there's some cutoff C-min where we're just not going to observe them. And then some region where there's a linear probability that we would observe a star, the star of that mass. And then one saying if a star's mass is greater than some C max, that we are going to observe them. Unless it died because of the stellar aging. Okay, so we can build in this completeness function into our likelihood, and then we can also incorporate measurement error. So in this case, we use log normal measurement error, And the point here is not to understand every aspect of this likelihood, but just to say that we can write it down. This first row is describing the stars that we're not going to observe. So due to the truncation, so the cutoff of the more massive stars, and then also the part that the lower end where we're not going to observe them because of they're not bright enough or massive enough for us to observe. And then this is defining the stars that we do observe.
Is n total known?
No, but we are going to assume it is known. So that could be another parameter though. But for now, we'll just assume it's known. Okay, so if this was the true initial mass function, then if we incorporate aging, completeness, and log normal measurement error, this is what we would observe. Sorry, they're on different scales. This goes to 60 and this goes to 16. But you see that on this lower end, things get cut off due to the probability of the linear completeness function is cutting off this part. And then due to aging, which it's not specified here, but I age at 30 million years, so that the more massive stars get cut off. Yep.
Those are still initial masses that are on the right. It's just the ones that we would actually see. They're not the observed masses that they would have today.
So yeah, great question. So this would be what we'd observe today. So this is what we want to make an inference on, the initial mass function, but this is what we have to use.
But when it says mass, is that still the initial mass?
The
mass of the star?
This is.
You would have like mass loss over time, things like that.
Oh, okay, yeah. So we're not. It's the same mass, but maybe with measurement error. Yeah, but yeah, we didn't account for depleting mass of a star. But that would be an interesting thing to include in the forward model, which one could include because it's a simulation model. So, okay. So what I'm going to show you then is what happens if we draw from the original likelihood, which we're just saying it's one part of the broken power law. I'm going to age the cluster 30 million years. I'm going to throw out values that don't make it based on this completeness function. And then I'm going to incorporate log normal uncertainty.
When you say you're going to age at 30 million years, you just mean you're going to apply those cutoffs?
Yeah, I'm just going to cut off the tail, yep. And then the prior we use is uniform from 0 to 6. And we use this just because in a different paper, they used an alpha between -6 and 6, uniform between -6 and 6, and it was going to be positive, so we just made it that. It wouldn't have made a difference if we used -6 to 6. Okay, so when we do this, now we have to figure out our summary statistics. How are we going to compare the data, the simulated and the real data? And one thing that we realized is we should account for the shape of the observed mass function. And so we have the simulated masses and the observed masses. And what we end up doing is taking the log of those masses, and then with the log of those masses, we do a kernel density estimate. And the reason we take the log is because there are some issues with the long tail. And so this just makes it so that the very massive stars aren't having a super big influence on whether a data set is accepted or not. So we just we look at the log masses, and we just do some sort of L2 distance between those functions. And so this actually looks very much like what we would have. We'd have an estimate on the log masses, and we smooth that, and we have the real data. And then we might just discretize this and do a pointwise squared distance, and sum them up and then compare them. Okay, so this incorporates the shape of the mass functions. But then it turns out because so the simulated data set and the real data set aren't necessarily going to result in the same number of stars. And so we learned this just from seeing that the ABC posterior was not matching the true posterior, that we actually have to account for the number of stars as well. And so we have a second summary statistic that says that the number of stars in the simulated data and the number of stars in the observed data set have to be the same. So we force that together as well.
Could you have just not normalized your histogram so it was counts instead set of frequencies and then a square difference.
So the problem is that the numbers that we observe are actually random because of the completeness function and the aging. So because that's random as well, that's containing actually important information. And so it's not just that the shape has to match, but the numbers have to be the same number of stars. So you're saying what if we just smoothed over the functions and or didn't normalize it, so it was a probability?
Yeah. So then if your simulated data produced more stars,
Mm-hmm.
all of the
It'd be shifted off. Yeah, that actually could be. That could be another. Yeah, that actually could be another way because that would then account for the number as well. So yeah, another good option.
Although there is an astrophysical implication of that. I mean, so I don't want to get you too far off track, but people talk about the fact that you can't break up a gas cloud into fractional pieces of stars, right?
Yeah.
So,
Mm-hmm.
like this is the argument behind the integrated galactic IMF.
Mm-hmm.
Like basically, the idea is that the in practice IMF of stars in a real galaxy is not the same as the theoretical IMF for a single gas cloud because
Mm-hmm.
when you take a real gas cloud, you break it into discrete stars,
Mm-hmm.
into fractions of stars. So it would be. I mean, if you're going to do it realistically, it would be important to sample discrete objects and not try to match on fractions of objects.
Yeah. So I think so. What he's saying is rather than what I do here because it's a kernel density estimate is I normalize it so that under.
I understand what you're saying. What I'm trying to say is that you can't. The real data has been affected by the fact that stars cannot be divided. The gas clouds can like if you take a gas cloud and turn it into like to give you a concrete example, a 10 solar mass gas cloud cannot make a 30 solar mass star.
Yeah.
And so there's zero probability in practice.
Yeah.
Even though your estimator is going to assign some finite probability of making a 30 solar mass star if you normalize.
Mm-hmm. Yeah, so all we need to do here, though, is we're comparing real and simulated data. And so even if we end up with probability in regions where it's not, it would have to happen in both for the distances to be close.
Okay, so you're saying your simulations will never make the unphysical stars and be accepted?
The simulations are just drawing stars of particular masses.
Right, and so they'll never make an unphysical distribution and be accepted, is what you're saying?
So that's the question that we're looking for with these summary statistics. And so even if it produces a data set that's not feasible, which I don't know how it would, but as long as it matches the real data set, then it's producing something that's close enough to something that is physical. And so all we're saying is it has to be close enough to what the real data are. So, okay. We because the numbers are random, we have to account for that. And then when we do this, this ends up being our observed mass function. We start with 1,000 stars. We use an alpha of 2.35, and we're only looking from 2 to 60 solar masses. I'm going to use 1,000 ABC particles, and I'm going to do this for 30 time steps. And when this we don't need to talk about that. So then what happens is this shows all the sequential posteriors, ABC posteriors. The true posterior is in red, and our final ABC posterior is in black, which you can kind of see behind the lines. And so it did end up matching quite nicely. And then additionally, what we looked at is if we generate a bunch of draws from our forward model by sampling values of alpha from our posterior, how well does it capture what the observed mass function is? So these are on log scales, but in black we have the observed mass function. And then this blue band is giving us a point-wise 95% credible band. And so, it's falling in this band. So that was good.
The blue is coming from your ABC. Your ABC.
Yeah, this band is coming from drawing values from alpha from our ABC posterior.
Mm-hmm.
And so we draw a value and then we throw it into the forward model and we get a simulated data set.
And it nicely.
And it bounds it, yeah. And I think, yep, so just in summary then, so side note, this was kind of one step which led to a more complicated forward model, but I just wanted to stop here to illustrate how you can incorporate different effects and how you can check or how you can compare the ABC posterior to a true posterior in order to get summary statistics, which would hopefully be useful in a more complicated model. And so in summary, yes, ABC can be a useful tool when your data are complex and you feel that writing down a likelihood is too much of an approximation, and you think that simulating your data would be a more reasonable way of understanding or inferring properties of your unknown parameters. But the selection of good summary statistics is crucial. And you really can get some bad, wrong answers if you don't spend time selecting good summary statistics. So I'll stop the slides with that. So thank you for your attention, and if you have questions, there you go. Thanks.
Well, I just want to thank you because this was a terrific presentation.
Oh, okay. Thanks. I like those questions.
And are you going to make this available online somewhere? Or?
Can I? Do you post them? Yeah. I can. Yep. And then also at the Penn State ASTRO Stat Summer School of 2014, I did 4 presentations on ABC and importance sampling, and then had a tutorial. So a lot of this comes from that as well. So that would be just another place. And you said it's astrostatistics.psu.edu. In 2000, Summer School 2014. Yeah.
Is there example code there as well?
Yeah. There's a tutorial. Yep. Yeah. So any other
I don't
questions?
suppose there are any tutorials in Python.
No, sorry. Yeah,
You can convert it into Python.
Oh, right.
yeah, I'd like to learn Python. I just have not yet. So. Oh yeah.
It's a package.
Is it?
Seriously?
You can call R from Python code.
Oh, well,
I'm sure it's.
yeah. So the tutorial, the point is to do it.
Yeah.
Okay, good point.
I think there should be. I think I comment it. Like I put comments. So hopefully it's at least clear what's going on in it. I don't know.
So you could write the equivalent.
Yeah. That would be the.
Oh, there you go, Charlie.
Yeah.
What if your forward model is wrong? Is there any way you can account for like the discrepancy between like the forward model and like your real but unknown physics model?
Yeah. Okay. So if your forward model is wrong, how can you? I mean, it's not an obvious thing. Like, so you want to have some extra discrepancy that's.
Like, so I always think of this as sort of like a complement to emulation in some way.
Yeah. Oh yeah. Yeah. Sure.
You can like include discrepancy terms to say that like, and not even that your emulator isn't a good approximation of your simulator, but that the simulator itself might not be perfect, and so you want to include that extra uncertainty in your final analysis.
Yeah. There's nothing that I've seen that tries to quantify some sort of forward model misspecification, but that's not to say it hasn't been done or that it shouldn't be done. So it could be an interesting thing to look into. I guess I don't have a sense of what they do with emulators. Like I often see like an additive discrepancy. I don't know if that would make sense to have an additive discrepancy, but yeah, maybe one could look at what they do with emulators and try to mimic it with ABC. Becky?
I can see why the summary statistic would fail if you didn't choose something that's like what you're actually interested in. Like if you chose the mean, but in fact, you don't. The physics that you care about is not really set. The mean's not the main thing that's measured.
Sure.
But
Yeah.
should you also worry that your summary statistic just doesn't work within this for some reason, even though it is actually what you care about? Like, what would cause a summary statistic to be? Would something cause it to be bad besides just that it's not really sensitive to what you're trying to measure?
Yeah, okay, so one illustration that I should actually incorporate this back in. If you're in the, even just a simple normal Gaussian case, and you're interested in the mean mu, it might seem reasonable to condition on, so we saw conditioning on the sample mean, and that works. And it might seem reasonable to condition on the median. Now, if you condition on the median, you're actually targeting a different distribution. And I can work out exactly what that distribution is because the median is an order statistic, so it's not the full data set. And so instead of, so we know that the true posterior conditions on the full data set, and conditioning on the mean is the same thing as conditioning on the full data set for a Gaussian. But if you condition on the median, as long as the median and the mean are the sample median and the sample mean are close, you're going to be centered in the right spot. But the median is going to be much broader. And so it might seem like
like you could add things at the end and it wouldn't really care.
Yeah, it's gonna be flattened. Yeah, and so you can write out what that is because the order statistics have known distributions, which are a form of a beta distribution. So you can work out what it looks like and see that it matches. So that's one way it can be bad. And if the sample median is different from the sample mean, maybe you have a small data set, then it can be biased as well, centered at a spot that it shouldn't be. So that's just a simple case where you might reasonably consider the median as a good summary, but it ends up throwing things off.
Okay.
Yeah. Yep.
So mathematically, did they prove that the sequential ABC or one of these ABC algorithms actually targets the true posterior? Is that true only if you have a sufficient statistic, or even if you don't have a sufficient statistic?
Yeah. So there's some kind of theoretical papers on ABC, and some of them at least just assume you have sufficient statistics or that your summary statistics are good enough, but not necessarily if you don't have good summary statistics, it's not going to work. Yeah, you won't be targeting the true posterior.
But if you have a summary statistic that's not a sufficient statistic, will you still be targeting the posterior?
Not necessarily. Yeah.
So is it really only if you have a sufficient statistic that you'll really be targeting?
Well, so the full data set is a sufficient statistic. So like doing something like a Hellinger distance between the kernel density estimate of your data seems to be pretty close to using the full data set at least. Doing some sort of comparison of the empirical CDF is basically using the full data set. And so Sheila, at the very beginning, you said, so are you comparing distributions? And in some ways, comparing the distributions is a good way of those would be good summary statistics with a good, as long as the distance is appropriate because you're using all your data somehow. There's a Hellinger distance, which so it's what is it? So you'd have two densities. It's the difference, the integrated distance between the square root of those two densities raised to
1/2.
Is it raised to 1/2? Okay. It's.
Well, wait. I'm sorry. Is it maybe squared? Maybe squared.
Yeah, I think it might. So.
Yeah.
Is it? It's like this.
And then the whole thing squared.
Is it the whole thing squared or within it squared? Inside squared. So this would be the kernel density. So we'd probably have to estimate these things.
So you have a KD of the data and a KD of your generative model.
Yep.
And then
Yep. And then maybe you discretize your space X, and then you can calculate. You can estimate what this is. So. So that's a Hellinger distance, and there are other sorts of distances like that.
For ABC, in 2014, there are 3 parts to the summer school. Look at the last one. Regular summer school. Another is statistical modeling of cosmic populations. Third one is Bayesian computing for astronomical data analysis. That's where Jessi's lectures are.
Okay. Yeah.
Just in practice, in practical applications, up to how high dimensional parameter space can you actually deal with in this? And is it easier or worse than MCMC in broad terms?
I would suspect it's worse. The highest dimensional case that a student is working on that I know of is around, like, I think there's like 24 parameters. But the issue is that if you have a lot of parameters, it seems you may need more summary statistics. And when you have more summary statistics, the convergence is going to be much slower because you're trying to shrink a lot of things in your steps. Like you'll either have a lot of epsilons, or you maybe combine it into one summary statistic. And so yeah, it does not seem as currently set up that it's very suitable for high dimensional parameter spaces. But yeah, maybe there are some ways of getting around that, but at this point, it seems like it's more for fewer parameters.
I mean, I could imagine a case where, suppose, for example, observational selection effects make it that could be part of your forward model, which makes it hard to write down an analytical likelihood function.
Yep.
But if I turn off the selection effect and say there's no selection effect, then I have an analytical likelihood function. So I could imagine a case where I could do my regular MCMC and generate samples from the posterior when that piece of that likelihood associated with the selection effect is turned off, like it's set to 1. And then to get the posterior when the selection effects are turned on, I would start with the MCMC samples I now have, and then use that to initialize some kind of ABC.
Yeah, so
starting from scratch.
Yeah, so you could use that as like your proposal instead, but you would still want to you still have to have importance weights to kind of offset it. So it kind of gets into what you were asking. What if you don't know the functional form of the posterior? So yeah, so you would just have to estimate some way, so your posterior that you're sampling from, be able to get functional estimates of it, which isn't necessarily a problem as long as it's not too high dimensional. You can just do a kernel density estimate and then get what would be in the numerator, or sorry, denominator.
Yeah, that's an interesting case where your likelihood function is composed of different parts. Some of them are analytic. You can evaluate them, but part of them are kind of separate from that, but are not analytic.
Yeah,
Maybe there's a better way to combine methods together.
Yeah, no, that's a great idea. Yeah, like if you know clearly one aspect, but there's some extra effects that are causing problems. Yeah, that's a good idea.
And there's 1/2 in front of it.
Oh, okay. Let's just be.
That's right.
But according to Wikipedia, that's technically the Hellinger distance square.
Okay. Any other thoughts, questions? And look, it's perfect timing, right?
Bus is leaving.
Yeah. I think it's like 6:45. Yeah. So, all right, great.
Thank you, Jessi.
Thank you. Thanks.